Welcome to the Heath video series soldering course. The overall objective of this course is to teach you what solder is, how it works, and how to use it. By using the techniques presented here, you'll be able to make good solder connections. Some of the world's most important machinery depends on fail-safe, intricate electronic circuits. Lives can depend on those circuits. All electronics, no matter how sophisticated, depend on a secure way of joining thousands of components. Fortunately, soldering is a simple, reliable way to make those connections. The composition of solder hasn't changed much in 100 years. Yet no matter how advanced our technology, soldering still has two advantages over any other joining method. It's a good physical connection. A soldered junction can be as strong as the metal surface itself. More importantly, solder is a good electrical connection with very little resistance to current flow. This is important in low voltage circuits. Solder is an alloy of tin and lead, mixed for a low melting point and good physical strength. When a solder ratio is written out, the first number is always tin, the second is lead. For example, 60-40 solder is 60% tin and 40% lead. Tin melts at 450 degrees Fahrenheit. Lead melts at 621 degrees. But most solder melts at a temperature lower than that of either tin or lead. The melting point of any solder varies with the tin-lead ratio. The horizontal scale in this chart shows several ratios, and the vertical scale shows Fahrenheit degrees. Now, look at the melting point for 50-50 solder. You can guess that its melting point is 414 degrees. All solder is solid at about 360 degrees. But there's a gray area between solid and liquid called the plastic state. When solder is plastic, it can be moved or molded, but it's not truly liquid. 60-40 solder has a plastic state range of only 10 degrees, which means it hardens very quickly. 60-40 also has one of the lowest melting points, 370 degrees. There are many ratios of solder for many uses, but because it melts at low temperature and hardens quickly, 60-40 is the solder used for 90% of all electronics work. After knowing what solder is made of, you'll want to know how it works. When solder is melted, it will behave like other liquids. It'll follow the path of least surface tension and flow over metal surfaces by capillary action. If the surface is clean, solder will settle in every pore and mix with the molecules of the surface, creating a strong bond. This mixing is called wetting, and it makes a good physical connection. The interface is the area where solder mixes with molecules of both the wire and terminal to lower resistance to current flow. This interface makes solder a good electrical connection. The self-review questions for this unit are in the workbook, so stop the tape, return to the workbook, and follow the steps listed in the activity guide. We mentioned that 60-40 solder is commonly used for electronics work. But solder alone won't make a good connection. You also need a compound called flux. This is because solder will not adhere to an unclean surface. You can scrape away dirt and grease, but a tougher barrier of oxidation will remain on surfaces that have been exposed to air. To chemically remove that oxidation, flux must be heated. And with the oxidation removed, solder can reach the copper on this surface. There are two kinds of flux, acid and rosin. But acid flux has two serious disadvantages. It's corrosive. Acid flux can damage foil or circuits on a circuit board. More seriously, it conducts electricity and can cause leakage between circuit paths. But rosin flux does not have these disadvantages. And with convenient rosin core solder, you can apply both the rosin flux and solder in one step. Rosin core solder is a simple but remarkable tool. The rosin melts just before the solder and cleans oxidation from the surface. Then the solder melts into the pores of the clean surface. Like acid flux, rosin is corrosive at high temperature. But when it cools, rosin is no longer corrosive and it does not conduct electricity. For these reasons, rosin is the only type of flux you should use on electronic circuits. Doing any job well means using the right tools. In soldering, this means choosing the right soldering iron. This is important because anything you solder acts as a heat sink. The larger the surface area, the more heat the object can absorb. A copper pipe will slowly soak up and dissipate as much heat as this iron can produce. But an electronic component has a small surface area and can't dissipate heat quickly. Too large an iron can scorch it in seconds. Many hobbyists own soldering guns which have two heat ranges. These tools are versatile, but they're not suited for most electronics work. Soldering guns are heavy and bulky. The trigger action requires reheating for each use. The tip is too large for the narrow spaces of the circuit board. And finally, soldering guns produce too much heat. A 25 to 30 watt pencil iron is the best tool for circuit soldering. The tip is narrow. You can hold this iron as comfortably as a pencil. And 25 to 30 watts produces a tip temperature of 650 degrees. This is the right temperature for 90% of all electronics work. The next section will explain how to keep this kind of iron working efficiently. Grease, burn flux, and oxidation build up very quickly on a hot soldering tip. A dirty tip transfers heat poorly and melts solder more slowly than a clean tip. It'll actually save you time if the tip is clean. So every time you use your iron, just wipe the hot tip on a very wet rag or sponge. Then you should tin the clean tip by applying a fresh layer of solder. This solder provides a barrier against dirt and oxidation and will keep the tip clean longer. The self-review questions for this unit are in the workbook, so stop the tape, return to the workbook, and follow the steps listed in the activity guide. To learn how to make a good solder connection, let's first look at some bad connections. The most common soldering mistake is not applying enough heat. The result is called a cold solder connection. A cold solder connection looks dull and crystallized. The connection will probably be physically weak and may have high electrical resistance. To avoid a cold solder connection, be sure to heat the solder above the plastic range. Plastic solder may seem to be melted, but won't be truly liquid and won't harden properly. Don't move the connection while the solder is cooling through the plastic stage. Any disturbance may prevent proper mixing with surface pores. Another type of bad connection, called a rosin joint, is caused when rosin core solder is not heated long enough for the rosin to boil away. The rosin may stay inside the connection and create an open circuit. You can easily see the difference between a cold solder and a good connection. A good connection is smooth and shiny. Solder has flowed evenly and settled in the surface pores. This means the solder has melted completely, then hardened around the wire without being disturbed. To correct a cold solder connection, reheat it and apply a little extra solder. To repair a rosin joint, reheat without adding solder. Watch for a bit of smoke as the rosin boils away. To solder a strong connection with low current resistance, follow these steps. If you're removing insulation, don't nick or scratch the wire. A weak wire creates a weak connection no matter how good you're soldering. Tack soldering to a flat surface requires a steady hand because there's no way to anchor the work. But whenever possible, it's a good idea to anchor components. This avoids movement while the solder is hardening. So bend wire leads around a terminal or bend wires slightly on a circuit board, leaving room for heat expansion. Don't anchor the component too close to the board. Clean your iron before applying solder. It only takes a moment and the work will go faster. Heat the work and the surface for 2 to 3 seconds. Both should be about the same temperature. Touch solder to the far side of the connection so heat will be drawn through the work to reach the solder. Let solder flow only until the connection is covered. The end of the wire lead should extend above the solder so you're sure there's a strong interface between the solder and the wire. Heat the connection only long enough to melt the solder completely. Let the solder flow evenly over the work. Before removing the iron, be sure that you see a small puff of smoke as the rosin flux evaporates. A heat sink will prevent excess heat from reaching sensitive components. Place pliers on the wire lead between the connection and the body of the component. This will draw excess heat into the pliers instead of the component. With these steps in mind, you're ready for a bigger challenge: circuit board soldering. The self-review questions for this unit are in the workbook, so stop the tape, return to the workbook, and follow the steps listed in the activity guide. Most modern electronic components are assembled on circuit boards that allow amazing complexity and compactness. But circuit boards also pose some of the greatest problems in soldering. One problem is the difficulty of soldering among the small components and circuit paths of a circuit board. So you should use an iron with a small tip. Apply only a thin thread of solder, just enough to make a good connection. Another problem is heat damage. Sensitive semiconductors can be scorched in a few seconds. Also, the adhesive that holds the copper foil can be burned and the foil can tear away. Unfortunately, heat damage often can't be detected unless the board is tested. The most serious problem can be the solder bridge, caused by using too wide a soldering tip or too much solder. The solder spreads out and runs between the circuit paths. A solder bridge can short out many components throughout the board. But if a bridge is detected before power is applied, this mistake can quickly be repaired. Repairing circuit boards is an important skill. Large soldering machines can solder thousands of connections per minute, but boards soldered by machine can still be repaired only by hand. The simplest repair method is to melt the solder and pull out the defective component. But this has disadvantages. Repeated heating may damage components or foil. It's difficult to pull wire leads while also holding the soldering iron. When the component is removed, the circuit is still plugged with solder. So the best repair method is to remove the solder completely, and there are many tools to help you do this. The most common is the vacuum bulb. When the solder is melted, you can suck it up by squeezing, then releasing this bulb. This convenient plunger can be used with one hand. A push of a button releases a spring mechanism. This creates a powerful vacuum that can often remove all of the solder in one operation. But be careful, don't let the plunger hit you when it releases. Even simpler, this iron has a vacuum nozzle as part of the tip. There are many types of vacuum nozzles available, including power-driven vacuum nozzles. One of them may be your best choice. But the simplest tool for removing solder is braided wire coated with rosin flux. When heated, flux cleans the braided wire. Then melted solder flows by capillary action from the repaired connection up into the braid. There are many reasons why professionals use braided flux for solder repair. It absorbs solder quickly and effectively. It's flexible and, if needed, can fit in tight spots. It can be a one-hand operation if the braid is held to the connection with the tip of the iron. Finally, it can be used in combination with vacuum tools. Once you've removed a defective circuit board component, follow these steps to resolder a good component. It's always a good idea to keep your iron clean. Push the component through the hole so the wire leads come up on the foil side of the board. Anchor the leads, but leave room for heat expansion. Heat the wire and the foil for 2 to 3 seconds so both are about the same temperature. Apply solder on the side of the connection opposite the iron so heat is drawn through the work to reach the solder. Remove the solder and iron after a small amount of solder melts and flows evenly over the connection. The last step of good soldering is inspection. If you look for mistakes after completing each connection, you'll save troubleshooting time in the long run. The solder on each connection should be shiny and smooth. Be sure each wire lead extends through the solder. This ensures enough interface area for a good physical and electrical connection. Apply pressure to the connection. This will help you detect rosin-insulated joints or cold solder connections. If there's any movement, the connection must be resoldered. And finally, look for solder bridges or loose solder that could cause a short circuit. We've shown you the basic steps of soldering and repairing connections. Before you answer the self-review questions for Section 4, there is one very important thing to remember: safety. Molten solder is extremely hot, and it can spill or splash like any liquid. A ball of solder could fly from a loose wire into your eyes. You could be easily burned. Soldering guns and irons are even hotter than the solder. If you handle equipment carelessly, you may injure yourself or someone else. So to protect your vision, wear safety glasses. And always treat solder and soldering tools with respect. With a bit of caution and practice, you can make soldering a safe and very useful skill. The self-review questions for this unit are in the workbook, so stop the tape, return to the workbook, and follow the steps listed in the activity guide. The previous sections of this course have explained the basic how-tos of soldering. Section 5 will show you some professional techniques. This section isn't covered in the soldering workbook because the movements are shown in real time. It's possible to show this movement only on videotape. This is the best way to solder individual components. First, connections must be clean. To help rosin do its job, you might rub away excess dirt with a pencil eraser. When soldering to a lug terminal, wrap the lead all the way around the lug. This maximizes heat transfer throughout the connection. Touch the iron to one side of the connection and the solder to the other. Wait for the lead and terminal to come to the same temperature. On circuit boards, anchor components by pushing leads through holes, then spreading them slightly. Don't push the component in so far that you crack the component. Leave enough room for heat expansion. An alligator clip makes a great heat sink. Also, it makes a good spacer that positions the component away from the board. Heat will be pulled through the connection and the heat sink, but it won't easily reach a sensitive component. A clean soldering tip is as important as a clean connection. Wipe the tip clean with a wet sponge so you see a silvery colored tip. Wipe the tip clean with a wet sponge so you see a silvery colored tip. Apply some rosin core solder. The rosin will break up the dirt, and when the tip is wiped again, the liquid solder will carry away the dirt so it won't be deposited in a connection. Just before using, apply a bead of solder to the tip. Experience and the size of the connection will tell you how big a bead to use. Too big a bead will put too much solder on your connection.
The reason for applying the bead is that it increases the surface area of the tip slightly, and more heat is passed to the connection. Also, liquid solder is a flexible, effective heat transfer medium. Place the tip so the bead contacts the greatest surface area of the connection. Experience will also teach you how long to leave the tip of the iron on the connection. This contact time depends on temperature of the tip, size of the tip, size of the solder bead, mass of the connection, in other words, how much heat it will absorb, how much surface area the iron contacts, and how much pressure is applied. Be sure there's a firm contact, but use a light touch. Normally, the right time of contact is about 2 seconds. Get to know the right amount of solder to apply, and apply enough so that solder totally encapsulates the connection. However, apply only enough so that there will be a point on the top of the connection when the lead has been trimmed. The solder connection should flare toward the bottom of the circuit board connection. The hardened solder should appear concave. Be sure the wire extends all the way through the soldered connection. This ensures a good physical and electrical bond. So that you don't burn components, use the minimum wattage iron that will do the job, usually 25 to 35 watts. Heat transfer depends on tip size, so some irons have interchangeable tips. When selecting a tip, consider the actual size of the area where you'll be soldering and the amount of contact area needed. More contact area on the soldering tip means more heat transfer. Also, consider the heat drained by the mass of the connection and the heat recovery time before the iron can solder another connection. With dual inline pin chips, space is very limited. To make insulation easier, insert one row of pins. Use a probe to align the other row. Be sure no pins are bent under the body of the IC. All pins should show through the other side of the board. Anchor the IC by carefully bending some of the pins from both rows. Use a small soldering tip because these pins are very close together and ICs are very heat sensitive. Don't drag the iron from one pin to the next because this can easily cause bridging. Pull the tip straight up. Notice how solder flows only over metal contact surfaces. If you use a minimum of solder, this feature will help you avoid bridging. Other professional techniques include tinning the end of the lead to keep strands in place. Use just enough solder to cover the wire. You should still be able to see the direction and twist of the strands. There is a method of tack soldering a bulky terminal that avoids the need for a third hand. Put a bead of solder on the pad. Put the ground lug or terminal in place. Apply heat to the top of the lug. Put on more solder and shape it with the iron for maximum strength. Because the mass is greater, the lug will require more heat and contact time. Hold it very still while the solder cools. When soldering coaxial cable, use the proper stripping tool to prevent nicking or weakening the wire. Don't put a bead of solder on the tip this time. Heat the outside of the phono plug pin. Notice how the capillary action pulls solder into the connection hole. Make a solid ground connection with a shield. Do not move the connection while the plug is hot. This will avoid melting the insulation of the center wire. On some circuit boards, the connection hole is plated with foil all the way through. This requires more heat and more solder because the connection has more surface area. Select a soldering iron and tip that will allow you to make the connection in about 2 seconds. You know you've used enough solder when a small bead forms on the other side. Once you've practiced these techniques, you'll be able to solder as quickly and effectively as this. You won't want these long wires exposed. Clip them so that the tip of the wire is still visible. Keep the leads from flying off when they're cut. They could hurt you or anyone near you. Then, carefully remove the clippings. They could cause a short between circuit paths. Always inspect your work before leaving it. Stress the connections and watch for movement. Even though rosin is not corrosive, it should be removed from circuit boards to aid inspection and improve appearance. Rotate the board to catch the highlights and watch for solder bridges. The connection should be totally encapsulated with slightly concave sides and flared at the bottom, which indicates good wetting. And of course, the solder should be shiny and smooth to indicate that proper heat was transferred and there was no movement during cooling. Also, before leaving your work, a bit of care for the soldering iron will keep it in good shape. For short storage, leave the iron on and covered with a bead of solder to stop oxidation and also to dissipate heat. For longer periods, tin the iron, wipe it off, then turn off the heat. For safety's sake, put the iron in a safe place where no one will touch it and it won't damage anything while it's still hot. By practicing the good techniques shown in this section, you'll meet the third objective listed in the introduction to this course. You will be able to make good solder connections. Connections that halt oxidation, have low electrical resistance, and are physically strong. This should be a good motivation to continue learning the art of soldering, to practice its skills, and to practice them safely.